Recall that our previous example involved tossing a coin 3 times, and the random variable x was the number of heads. So a success was a head when we tossed the coin 3 times. And the outcomes and the probability distribution we created with the outcomes and their probabilities looked like this. Okay? So that is a probability distribution. It meets the requirements of a probability distribution. Requirements say that the sum of the probabilities must equal 1, and we can see that they do there. 1 plus 3 plus 3 plus 1, that's 8 eighths, or 1. And that each individual probability is between 0 and 1. So 1/8 is between 0 and 1, 3/8 is between 0 and 1. And we've got each one of those twice. So we might ask the question, what's the average number of heads if we repeat this procedure an infinite number of times? Well, that's like saying, what's the mean of this random variable? So the mean, mu, would be equal to the sum of all the x's, all the different outcomes, times their probabilities. Okay? Well, given that, we can use the table to continue to calculate and get this mean of our probability distribution. So let me extend my table because I've got x and I've got p of x. So if I just extend it to include a column, whoops, of x times p of x, and then if I add those up, that's that sum of the x times p of x. So this will give me a nice way to get that sum. Alright, so 0 times 1/8 is 0. 1 times 3/8 is 3/8. 2 times 3/8 would be 6/8. And 3 times 1/8 would be 3/8. Okay, so now we want the sum of this column. So 3 plus 6 is 9, plus 3 would be 12. So the sum, in this case, of the x times p of x, we said would be 12/8. And then we could simplify that if we wanted to a decimal, and that would be, what? 8 goes into 12 and leaves 4, so that'd be 1.5 or 1.5. So now, what are we saying? We're saying that if we repeated this procedure an infinite number of times, that the average number of heads we would get would be 1.5. Is it possible to get 1.5 heads? No. But what this does is it gives us a good feel about what to expect in the long run. What's that measure of central tendency? Where does the data tend to center around when we're running this procedure of 3 heads? Okay, so of counting the number of heads in the 3 tosses. Okay, so the mean that you get from a probability distribution, especially these discrete probability distributions, may not be discrete results, and so therefore not possible. But that's not the point. The point is to give us some idea of where the data would center around if we did this repeatedly for an infinite number of times. And what we find is that as the number of repetitions of the procedure increases, the mean of the observations will approach the true mean of the random variable. Okay, so another name for mean, let's make a note of that. For the mean is expected value. So we'll be hearing more about that, expected value. Just another name for the mean because it's the value we'd expect if we ran this procedure an infinite number of times. Okay, so now we know how to find the mean from a probability distribution. We just take our possible outcomes, multiply them times our probability for each outcome and then sum that column. Now we want to find the standard deviation of this probability distribution. Recall that the population variance is sigma squared and the standard deviation is sigma. So if we can find the variance, then we can just take the square root to get the standard deviation. So the formula for variance, sigma squared, for a probability distribution is the sum of all the random variable x's squared times their probabilities minus the mean squared. So we have to have the mean in order to do this. But now instead of x times p of x that we saw up here, it's x squared times p of x. Well, I don't have that yet. I don't have a column of x squared times p of x that I can add up, sum up. So I need to do that. Okay, so I'll just extend my table. Move it on over here so I have a place below to do my sum. Okay, so now what I want is x squared times p of x. Okay, so x is 0. 0 squared is 0 times 1/8 is 0. 1 squared is 1 times 3/8 is 3/8. 2 squared is 4 times 3/8 would be 12/8. And 3 squared is 9 times 1/8 would be 9/8. So now I want the sum of this column. So when I add those up, we get, and let me write it like I did under the mean, the sum of the x squared times p of x ends up being what? 3 plus 12 is 15 plus 9 is 24. And that simplifies to 3. Now this isn't the variance, this is the first part of the variance here, this part of the calculation. So now I know that the sum of the x squared times p of x is 3, so I can come down here and say, well, I've got 3 minus mu squared. Well, I found mu already. Recall that was right here. This was my mu, where we worked that out. So minus 1.5 squared. So that's 3 minus 2.25. Whoops, 3 minus 2.25. See if I can fix that real quick. This should be a 3. Okay. Or 0.75. Okay. Now I've found the variance, but what we want is the standard deviation. So, to get sigma, I just take the square root of sigma squared. So, the square root of sigma squared is 0.75. And when we get that, we get 8.860254. And on and on. I just stopped there. Okay, so we need to have a plan for numbers like this, and there is a rounding rule for the standard deviation and sigma, and the standard deviation and the mean. So let's write that. The round off rule for mu and sigma says that we will round our results to one more decimal place than used for the random variable x. Round to one more decimal place than used for x, our random variable x. So how many decimal places did we have in our random variable? Well, this is a discrete random variable, so they're always going to be integers, and therefore there will be no decimal places. So this is telling me that for my mean and my standard deviation, I need to round to one decimal place. Okay, so what we found for the mean, well, it actually terminated at one decimal place, 1.5. What we found for the standard deviation, I need to round to one decimal place, and this would round to 0.9. Okay, so now an important part of this is to come up with my interpretation of my results. So here's my interpretation. I would be saying that the mean number of heads in 3 tosses is 1.5 heads. The standard deviation is 0.9 head. Okay, so this is how we find the mean and the standard deviation of a probability distribution.